networks lecture. I'm super excited for this lecture because after discussing supervised learning topics and unsupervised learning topics, we're finally at reinforcement learning. Neural networks is our first stepping stone to understanding things such as deep learning. There's no official reading assignment for this lecture, but I would still suggest you go ahead and browse through the Wikipedia articles on neural networks and reinforcement learning before viewing this lecture. Let's go ahead and get started. Neural networks are modeled after biological neural networks, an attempt to allow computers to learn in a similar manner to humans, through reinforcement learning. There's lots of use cases for neural networks. A few examples would be things like pattern recognition, time series predictions, signal processing, anomaly detection, and later on, through the use of neural networks, you can even do things like controlling self-driving vehicles. The human brain has interconnected neurons with dendrites that receive inputs and then based off of those inputs produce an electrical signal output to another neuron. And that's the concept we're going to be trying to recreate through artificial neural networks, or ANN. Let's talk about why we want to even develop neural networks to begin with. There are problems that are difficult for humans but easy for computers. Things such as multiplying two large numbers together are easy for computers to solve but difficult for humans to do in their head. Then, there are problems that are easy for humans but difficult for computers, such as recognizing pictures of people or given an image and describing the image and what's inside that picture. Neural networks attempt to solve problems that would normally be easy for humans but hard for computers. Let's start by looking at the simplest neural network possible, the perceptron. A perceptron consists of one or more inputs, a processor, and a single output. A perceptron follows the feed-forward model, meaning that inputs are sent into the neuron, are processed, and then result in an output. So for this figure below, you would read this from left to right. You have input 0, input 1, going into the preprocessor and then being outputted as some sort of result after being processed. A perceptron process follows four main steps. First, you receive the inputs. 2, you put some sort of weight on those inputs. 3, you sum those inputs. And then 4, you process those inputs and generate some sort of output. Let's go ahead and walk through a very simple example. Say we have a perceptron with two inputs. We'll say input 1 is x1 equals 12, and we'll say input 1 is x2 equal to 4. Each input that is sent into the neuron must first be weighted, which means it's going to be multiplied by some value. Often this value is just between -1 and 1. When creating a perceptron, we'll typically begin by just assigning random weights. In this case, we'll go ahead and randomly assign weight 0 to 0.5 and weight 1 to -1. That means we take each input and multiply it by its weight. That means we'll say input 0 times weight 0 is 12 times 0.5 equals 6, and input 1 times weight 1 is 4 times -1 equals -4. The output of a perceptron is generated by passing that sum through some sort of activation function. In the case of a simple binary output, that activation function is what tells a perceptron whether to fire or not. There are many activation functions to choose from. Functions in processing such as logistic functions, trigonometric functions such as sinusoidal functions or tan functions, step functions, etc. Let's go ahead and make the activation function the sign of the sum, so a very simple activation function. In other words, if the sum is a positive number, we'll have the output be 1. If it's a negative number, we'll have the output be -1. One more thing to consider is bias. Imagine that both inputs were equal to 0. That means any sum, no matter what multiplicative weight you put on it, would also be 0. That would cause problems because it'll be very common to have a point that may just happen to land on x1 is 0, x2 is 0, or x is 0, y is 0, etc. In order to solve that problem, we add a bias. This third input is known as a bias, and it starts with a value of 1. This avoids that 0 issue. To actually train the perceptron, we use the following steps. We provide the perceptron with inputs for which there is a known answer. We ask the perceptron to guess an answer. Then we compute the error, which is basically asking how far off from the correct answer are we. We adjust all the weights according to that error, and we return to step 1 and just keep repeating this process. That means these 5 steps laid out here is how you actually train the perceptron, and you'll basically layer a bunch of perceptrons and create a neural net. We repeat that until we reach an error that we're satisfied with, and you usually set that beforehand. That is how a single perceptron would work, and now to create a neural network, all you have to do is link many perceptrons together in layers. You'll have an input layer and an output layer. Any layers in between are known as hidden layers, because you don't directly see anything but the input or output. You may have heard of the term deep learning. That's just a neural network with many hidden layers, causing it to be deep. You may be wondering, well, how deep is a typical deep learning network? There's no good answer for how many hidden layers you should use, but as a quick example, Microsoft's state-of-the-art vision recognition uses something like 152 layers. Let's go ahead and go to RStudio and begin to explore with an example. Then finally, you'll have a project to test your understanding of creating neural networks in R. Thanks everyone, and I'll see you at the next lecture.